Okay, let's talk about hash functions. Hash functions are one of the most important kind of cryptographic tools that we're going to need to use when designing smart contracts. So the basic idea of a hash function is that it's a function that's easy to compute and everyone can agree on, that takes in arbitrary size strings as inputs and always produces a fixed size output. We'll be using a couple of standard hash functions like SHA-2, which has a fixed size output of 256 bits, regardless of the size of string that you give it as input. Now, hash functions are chosen for their security properties, which we'll talk more about in a little bit, but for now, the important thing is that you realize that they kind of act like a random function. It's easiest to explain what I mean by that with an example. So we can go load up any website. There's lots of different instances of the source code for hash functions. They're standard, so they're fairly clear and well agreed upon, and you get the same value no matter how you compute them. So in this example, if I put in my string here, in this case, hello world, and hit calculate the SHA-2 hash, I get this string, which is 32 bytes long in hex there. Now, as you can see, this 32-byte string doesn't seem to have any discernible pattern in it. Doesn't look like it has a copy of hello world in it. And we can make this sort of looks kind of random notion even more, stronger by realizing that even if I change this string by one character, like adding an exclamation mark, when I compute the hash again, it looks like all the characters of the hash change. It looks like I get a completely different, completely new random hash. This seems to be true even as I add one character at a time. I get a completely different looking hash. Okay, now let's talk a little bit about how hash functions are used in computer security. Now these are used all over the place, so this is just one simple example of how they're used. So this is the idea of fetching a large file from an untrusted mirror. So let's say that you want to receive a file. You're going to get the file from me, and you trust me. But let's say that I'm not able to transfer a large volume of data to you, just about the size of information that could fit on a business card. So the idea is that I could include the hash of a file rather than the file itself. Remember that the hash function can take in arbitrary size strings. It doesn't matter whether it's a gigabyte or a terabyte. Anyway, I could take just the hash of this file, which is still just going to be a 32-byte fixed string, and include that on the business card that I'm able to send to you. Now, you can't get the entire file from me, but because you have the hash, you can download the entire file from some untrusted source, like a node on a peer-to-peer network or somewhere else. Now, the idea is that when you get this untrusted file, you recompute the hash for yourself and check that it matches the hash that's on the business card that you trusted because I gave it to you in person. Now, let's think about why this works. Assuming that the hash function is effectively a random string, then it's unlikely that I'm going to be able to find another file, or that the untrusted node would be able to find a different file other than the one that I had in mind when I gave you the hash of it, such that it's a different file, but when the recipient goes to recompute the hash, they find that it matches. This would be considered a collision, and hash functions are chosen because they're thought to have collision resistance properties. Now, this is a bit interesting because just by pigeonhole principle, there must be a large number of collisions. The output of the SHA-2 hash function is exactly 32 bytes, but I'm saying we can put files through it that are much larger than 32 bytes and still claim that we have this collision resistance guarantee. So this is interesting because, or this is plausible because the output space of 32-byte digests hash function values is still a really large space. And because the hash function is effectively random, there's not really a better way to find collisions than to go through a brute force search of the space of the hash function output space. Here's another use of hash functions I think is pretty cool. It's the idea of creating a visual hash function. So the idea here is that we can take a string and evaluate the hash function of it, and use the bits of the hash that results to select some attributes of a little 2D illustrated image. So in this case, when I type Andrew, I get this gray robot. If I type in Andrew Miller, I get a robot that has completely different attributes, different color, different face shape. Now the idea here is that if this is a standard, then I can use this visual hash to check whether or not some file that I have matches some string, or whether or not I'm using the right public key for someone I'm trying to contact. Now this makes sense if you assume that humans are going to be good at discerning small differences between robot pictures that they've remembered, or between comparing two hashes, more so than just comparing the random strings directly. You see something like this also used in MetaMask and Ethereum. So these little icons that are generated along with your account, they're actually functions of your address. So as you switch back and forth between different accounts, you'll always see the same icon when you're on the same account. And this holds even if you go revive your wallet by loading the backup key on a different computer. So it's the same kind of visual hashing idea in MetaMask as in RoboHash here. Okay, so here's one kind of subtle issue with hash functions. Thinking of a hash function as a random function still has some limitations. So for example, you might imagine that we could use a hash function as a kind of encryption. So for example, if I think of a word that I want to use as a passphrase, let's go with underdog. And I look at the SHA-2 hash of this, well, there doesn't seem to be any relation between this set of random 32 bytes that look like a random string and this password that I want to represent. However, if you then go and do a Google search, for example, for this hash function, you'll find that there's already people who know that this hash function decrypts to the word underdog. How bizarre is that? Well, what's going on here is that even though the space of possible hash functions that these random strings seem to be drawn from is really large, there's already people who have guessed all of the likely passwords or all of the dictionary words, all of the simple variations of dictionary words, and have already built lookup tables of all of the resulting hash functions. So even though the space of the hash functions is large, if I'm trying to get a privacy guarantee out of providing input from a fairly small space, like all dictionary words to the hash function, then I'm going to have some kind of a security problem in that assumption. Okay, that's all about hash functions for now. In the next video, we're going to look at some more examples of how we use hash functions to achieve some security goals in smart contract programs.